Hello everyone. As you know, we are about to start a course on bare metal embedded system in the coming 16th. So I was getting so many questions and queries related to the syllabus, the content and the timings, also about the fees. There are so many questions I was getting related to the course. So that's why I am creating this video. So in this video, I will be explaining the syllabus, how we are going to uh, cover the topics and what all we are going to discuss in the 6 months, and how we are learning the bare metal coding, and what is why I choose the RISC-V as a microcontroller. I mean RISC-V as the core of a microcontroller for understanding bare metal coding. So this course is planned for 6 months, total 24 weeks, with hands-on coding experience. You will get hands-on coding experience. So maximum students I am allocating is six. The class duration will be uh, 2 hours. Initially, I thought of giving 1 hour, that is insufficient. So it is 2 hour in a week. That will be on Sunday evening. Maybe I will be scheduling at 7 or 8. If 7, if the class starts at 7, it will stretch up to 9 p.m. So let's move on to the uh, next slide so that I can explain uh, what are we covering in the course. So, before understanding the coding, there is a question now roaming around in the AI era. In the AI era, why we are learning how to code? Why we learn to code in the AI era? So, look at the comments from uh, the leading uh, entrepreneurs around the world, Satya Nadella, uh, Jensen Huang, and Dario Amodi, and Sam Altman. You know who is these persons. So everyone is telling the coding is not going to die. See, AI is already writing 20 to 30% of the code in our repository, and the percentage is only going to grow up. That doesn't mean that that doesn't mean that there is no role for developers. The role of developer is mainly focused on architects. So it is the role of developers to architect the code, not directly writing the code fundamentally. So what is the core concept? The core concept is that developers focus should be on the architecture perspective. So the developers should develop code uh, based on the architecture. So developers should invest time on finding solving the engineering problems, automates, and debugging the system, reviewing the code, solve real world problems, as I said already. So this is the thing. So we need to learn the code. Without learning the fundamentals, we won't be able to progress in the AI era. Of course, it is sure that AI is going to help you write the code. If you are telling AI to write a blink LED code for a particular microcontroller, say STM32 PIC or our RISC-V, it will write the code in a fraction of second. But whenever there is some issue while flashing the code, while upgrading the code into some multiple pins, you need to understand what the code is actually doing. Then only you will be able to debug the system. So the responsibility of the developer is now switched to uh, now focused to into architecting things. So in order to architect things, you need to know the fundamentals of coding. So we are covering in our course from the basics itself. We are learning the architecture of the microcontroller or the SoC. We are taking a particular microcontroller in our course, which is Pico 2, which has 4 cores inside. At a time, it can work on either 2 ARM core or either 2 RISC-V core. So that's it. So if AI writes more code, what I have already told, fundamentals matters more. AI can generate, yes, uh, AI can create functions, AI can create tests, AI can document, AI can boilerplate. Uh, so AI can do most of these things, but you will need to understand the CPU architecture, memory, registers, protocol, timing, etc. in order to have a good understanding of the architecture. So you must do what what is the issue. You must know how to understand and debug the things. You must verify, you must debug. That is the thing. AI will do the code generation part. So does the code you the question is like this: you must verify, does the code configure the hardware correctly? See, AI will be writing the code, but you need to ensure the code configuration happened properly. Does it meet the timing? Does what happens if the code fails? And then you must debug the read registers, analyze faults, trace execution, find root cause, fix the system, analyze the waveforms from oscilloscope. You try to understand use of function generator and um, logic analyzer. So the responsibility, as I said already, the responsibility of the developer is more focused on the debugging and architecture perspective. So then the another question from some group of people: why learn RISC-V? RISC-V is more than another CPU instruction. You know, right? Like uh, we already heard about ARM. That is an another CPU instruction set, and you already know about x86. That is another set of ISA instruction set architecture. But there is a benefit when we are learning RISC-V. The first benefit is it's open standard. The ISA specifications are openly available and maintained by RISC-V International. Openly available means you will be able to see the RTL code, you will be able to uh, see the ISA instruction sets and access all those documentation inside the core itself, inside the RISC-V core itself, and it is modular. A base ISA can be combined with standard extensions, and it is extensible. Architecture support custom extensions, like you can as you see, many chips are coming uh, in this era with RISC-V as the core. So RISC-V becomes the center of the SoC, and associated peripherals come different vendor. This multi-vendor architecture comes in this perspective. So the same open ISA can be implemented by different hardware vendors. Maybe for an example, Infineon can have their own associated peripherals with them. They can use this open source RISC-V to make a microcontroller. So this is an example. So why we learn RISC-V is that it is an open source architecture, and we have complete access to that RISC-V core. That is the reason why why we choose RISC-V. So the main point is open standard and ratified specification. So learning RISC-V gives you architecture level skills. So as I said, AI creates code. You need to test, debug, deploy. So the responsibility is becomes architecting the system. So you need to understand the CPU. You need to understand registers, instruction formats, assembly, calling conventions, CSRs. Under the system, you need to know the boot flow, how your SoC boots up, how a CPU boots up, the memory map, exceptions, interrupts, privileged models. Build low level skills like how to write a startup code, linger script, drivers, debugging skills, performance analysis. So we are learning all these things with the help of our RISC-V code. So these are the transferable embedded system concept. But you are using Pico 2, Pico 2. So Pico 2 has ARM and RISC-V. Our course is focused on RISC-V, but after completing the RISC-V course, the concept stays same. So this is transferable embedded system concept, which means after learning the RISC-V course, you will be able to apply the same concept and skills on ARM core as well. You have to try it after the if you are joining the course after completing the course 6 months. You need to try understanding the RISC-V principles also. You need to uh, extend your knowledge on ARM as well by utilizing your concept learned from this course. So this course not only stays in RISC-V. This is a fundamental course which is applicable everywhere. Again, the slide explains why RISC-V. So it connects software development with the processor and the silicon level thinking. So you are writing an application code. Application logic is written in C language, which controls the registers. So hardware control is happened with the help of registers. So register actually handles RISC-V core, which is the CPU, and the that is collectively called drivers. So there is a hardware software interface called drivers, which is the software actually controls the registers and CPU in order to have a properly executing application logic. So after that, if there is some issue, there should be a root cause analysis, debug should happen, then the system integration happens after the throughout the development, debug, application development. So the system integration part comes at the end. This is a collective in nature. So integration means we are writing the application code, hardware, and if some issues are there, we are finding the root cause, and debug happens. We are providing the fixes, and the system integration continues. So RISC-V helps expose the boundary between software and hardware because the contents are uh, open source. So focus architecture understanding, developer driver development, and system debugging. Moving to the next slide, why does this course start with the RISC-V? So why does the course start with RISC-V? That is actually explained one. So giving the more picture, as I told, AI can write C code, driver skeleton, register definition, test code. But as I it's a deeper explanation. Engineer must know if the register is correct, is the sequence correct, what does the CPU do, what happens on failure. The course, the course teaches RISC-V, bare metal drivers, debugging, and system integration. As AI becomes a productive tool while fundamentals remain your engineering foundation. So engineering is always there, even if AI is being the productive tool, engineering still remains the same. So that is the um key takeaway. Like you need to understand the fundamentals. So, RISC-V CPU architecture, what are you going to actually learn? So, CPU architecture, we will be learning CPU architecture, memory, boot flow, startup code, and linker script. Then we will we will start building right register level drivers in embedded C for GPIO, UART, SPI, I2C, ADC, and PWM. These are the backbone peripherals of most of the embedded system application. So once you master all these fundamental peripherals, you can go for the bigger peripherals, bigger communication peripherals like USB, PCI, and advanced application development, driver development, maybe RTOS based and Linux based driver development as well. This course becomes a concrete pillar for your future embedded system aspirations. So debug using interrupts. You will be learning how to use interrupts, CSR, GDB, and DMA, PIO, and dual core programming to build real embedded systems. So and you will be learning the flow, how actually SE code being compiled and um, driven hardware driving a hardware. So embedded C code, the compiler compiles it and startup code boots the system, register you are controlling the register driver, and you are creating the driver, and the driver drives the hardware. So this is a general flow. You will be learning all the internal concept of each and every aspects of all these things. First, understand the processor. So we are using Pico 2. Pico 2, as I said, Pico 2 has ARM Cortex M33 core, two numbers, and RISC-V Hazard 3 core, two numbers. So it's a four core device at a time. Two cores are able to help you at a moment. So we will be able to we will be learning how to configure those cores, how to choose those RISC-V and ARM cores. Understand what happens before main. So these are the core concept. We will be discussing boot, memory, linker, and startup. These are the core embedded software concept. And we build drivers for UART, SPI, I2C, ADC, and PWM. Then we move beyond basic peripherals, DMA, PIO, and multi-core. Use both hazard 3 core, shared memory, FIFO, synchronization, spin lock, and race condition. These are the advanced concept which will help you while learning RTOS and Linux based things. So multi-core concept also we are discussing. Also, we will be debugging using GDB, and we will be using GDB with the help of breakpoints, watch point memory, and register inspection. So these are the things an essential embedded system programmer must understand. Also, uh, we will be learning the fundamentals of unit testing, assertion, driver abstraction, and regression testing. Only fundamentals we touch, and progressively you will be learning register level GPIO, interrupt with the UART console, multi-protocol interface, SPI to CADC PWM, then data acquisition using DMA. Final embedded system, we will be constructing a project, as I mentioned in the syllabus. Yeah, the final goal is to build a complete bare metal system capstone project. From this course will help you to have a complete understanding of the thing. Also, we will be maintaining a Git repository for our course. You have to contribute, you have to show your contribution there in that repository. So, uh, what will you be able to do after 6 months? So, these are the main things which I have noted out for you. Uh, if you complete this course successfully, you will be able to write a bare metal embedded system for C for RISC-V, and all the other other course. Not only RISC-V, you will be able to, if you learn the fundamentals properly, any core coming in future, any core present in this era will be an will be a cakewalk for you. Like it should be easy for you. Once you learn the concept, it will be easy for you to program any microcontroller, any core. So understand, you will be able to understand RV32 architecture from this course, write and modify startup code and linker script, also make file, develop usable register level peripheral drivers, configure interrupts, exceptions, DMA PIO hazard, debug firmware with GDB, structure, test and document a professional embedded firmware project. So in the first month, we will be learning the fundamentals like C programming and RISC-V architecture. In the second month, we will be discussing bootloader, linker and assembly codes and startup code. Um, and the third month, we will be starting with our core peripherals. Fourth month, driver plus IRQ interrupt services and its usage. Advanced IOs for communication. The 6 months will be system level multi-core GDB testing and our capstone project. So this is the roadmap. So who should take this course? Anyone who loves to learn embedded system can take this course. So the main focuses are beginners or students who want a structured path into the embedded C and bare metal programming. Embedded developers who wants to excel their skills in registers, driver and interrupts and debugging, and RISC-V learners who wish to switch from some other core to RISC-V. So yeah, this course is mainly focused uh, for all of these people. Mm, it is planned in a way that anyone can join, maybe a beginner plus intermediate level people. This course is focused for a beginner plus intermediate level. So don't just learn to use microcontroller, learn how the processor, memory, registers, drivers and firmware work together. So that is the plan. And many people asked about the course fee and number of people. The number of people is limited to only 6, and course fee is one time payable 3,000. If you are facing any difficulty in paying one time, you can contact me. There is a We can find out a way in to pay it in EMI as well. So thank you so much. Hope you will find a suitable time and pace to learn fundamental soft embedded system using RISC-V. Thank you so much.